type of stuff. So I'll leave you guys to investigate that a little bit later, because we're going to move on here. Okay, so let's get into some logarithms next then. All right, so just a little review again. Like I said, there's some logs that we've looked at in the past. But before we can get into what those are, let's define log real quick, because there's some restrictions we have on how or what numbers we can use when we're working with a log. So logarithms always come in this kind of variety, a log base A of x. Like I said, there's some restrictions on it as far as what the base is that you can use. And this all stems from what numbers we're allowed to use in exponentials, because a log comes from an exponential, which we'll discuss more in a minute. But basically, be greater than 0, and A can't be equal to 1. Okay, now the reason for that, like I said, if I'm going back and forth between a log and an exponential, if this is the log equation, then the exponential equation from whence it came is going to be A raised to the y equals x. And we got those same restrictions on A. A has to be greater than 0, and A can't be equal to 1. So can we make sense of that, of why those two restrictions are there on A, based on what we've studied about exponentials up to this point? Consider each case individually. A greater than 0. What if A wasn't greater than 0? What if A was something negative? Okay, what would happen if A was negative here? Would it, when we graphed it, would it still make that nice exponential curve going up? What would happen to it? It would keep going back and forth, right? Positive, negative, positive, negative, because as soon as you keep raising that base to a higher and higher integer, it's going to flip-flop back and forth. And so it doesn't really follow that exponential pattern anymore, okay? What if A was 0 itself? What's bad with that? It just, right, it just stays 0 all the time, right? 0 to some power, it's still just 0. So it'd just make a flat line. That's not exponential, right? And what if A was equal to 1? What's the problem with that? It'd just be 1, right? 1 to any power is still 1. So that wouldn't be exponential either, just be this nice flat line, okay? So we got to have those restrictions on the exponential, and because the log comes from that exponential, we have to keep those same rules for A. Can't be, or yeah, has to be greater than 0, can't be equal to 1. Okay, so to know. Okay, some special logs that we use, that these should be somewhat familiar. The natural log, and this is simply where the base is equal to e. That's one that we'll use quite often. And we also have what's called a constant log, which just looks like this with no base, log x. And in that case, the base a is equal to 10. So, like I said, you've seen those before, but just to do a little refresh here for you. Here. These are going to be useful for you, not only right now just working with logs, but later on when we start working with derivatives and integrals and really get into the calculus. One thing we're going to want to do is to take an equation we're working with, like if we're trying to find a derivative or integral of some function we're looking at, more often than not, we're going to want to simplify that thing or change it to something else that will allow us to do those calculations. Because sometimes in one form you can't do it, but as soon as you switch it, write it in a different form, then you can do whatever it is you need to do. So these problems we're going to end up using quite a bit with that. So first one is a to the log base a of x. If you raise something to a log, okay, you're doing the exponential of a log, and those are two opposite things. They cancel out. So what is this equal to? Just x, right? Okay, so that's showing you that those two operations are canceling each other off. It would just be the x then. And what about if you have log base a of a to the x? So you're taking the log of an exponential now. What about that? That one also comes out to just x. Those two operations cancel each other out. Works same way if you're doing natural logs. I mean, they're both the exact same. It's using a base of e, but it's good to kind of see it. E to the natural log x is also just x. It's the same rule. And the natural log of e to the x is also just x. Works the same way. Okay? So those are some inverse for the exponential and the log, okay, because they're inverse operations that are going on there. Okay, some other logs that you guys studied quite a bit in Algebra 2 as well as pre-calc that it's worth noting. Like I said, I'm not going to delve too deep into these, but they should look familiar. First one is the product rule. So with the product rule, so if I have the log base a, it's y. Anybody remember what we can do with that then? Kind of break it apart into an addition problem. Yep, that's the product rule. And it goes both ways, obviously. So if you have two logs that are added together and you would like to bring them together into one, which usually will be, you can do that. If you understand the product rule, the quotient rule is pretty straightforward then as well. So if you have the log base a of x over y, what's the only thing that changes? Yeah, it's just a subtraction then. And then the one we're probably going to use the most, the power rule. And this one was log base a x to the y. Anybody remember what we can do with that? If we have a log of something raised to a power? We can bring the power down and multiply. All right, so let's see. So if we can use these properties at all to help us solve some problems, that's going to be kind of our last goal here with this stuff is, can we solve equations involving exponentials and logs and that sort of thing using some of these problems out. So let's say we've got So how about 2 times 5 to the x plus 2 equals 20? So if I want to solve this for x, first thing I'm going to need to do is divide by the 2. So we've got 5 to the x plus 2 equals 20. Now there's 2 different approaches to this. 10, oh, right, 10. Thank you. Mr. Herrick hasn't had his coffee yet. Okay, that's 10. So next thing we need to do, like I said, there's 2 approaches to it. You can either think about applying a log to either side of the equation, or you can think about taking this equation and rewriting it as a single log equation. Okay? So I'll show you both ways. Whichever you like best, go for it. I'll tell you which one's my favorite. So if you apply a log, you'll need to make sure you use the same base as the exponential side of your equation. Get that. Log base 5 of 5 to the x plus 2 equals log base 5 of 10. I put a log base 5 on both sides. Okay? Using our, what's going to happen right here on this side? We'll just end up with x plus 2, right? One of those inverse properties or whatever. It's going to cancel out. Exactly. I used a 5 here because this was a 5, and I knew that would cancel it out then. Okay, but I got to make sure I keep my log base 5 of 10 over there. Okay, and then solving for x, x is equal to log base 5 of 10, that quantity, whatever it is, minus 2. So if I was looking for an exact answer, there you go. You can just leave it like that. More often than not, we're going to want a decimal for this thing. So we're going to have to actually evaluate it. Now, to evaluate this log here, we're going to have to use the change of base formula. See if you guys remember this. Because your calculator doesn't have, well, some of the new ones do, but most of the old ones won't allow you to do a base of anything other than 10 or e. So the change of base formula allows us to turn this into a division problem. So it looks like that, okay? And that should be somewhat familiar to you at this point. So in any event, log 10 divided by log 5 is 1.43. And then if I subtract 2 from that, x is negative 0.57. Okay, so that's using the applying a log type process there, okay? So if I went the other way with it, which is just turning an exponential equation into a log equation and kind of working from there, that's another way of looking at it. Students in the past, I don't really like this way because they have a hard time remembering the conversion from one to the other. It's an important thing to know, but if you can get around it by doing this other process over here. But if you can remember it, I think it has a little less work involved. So it would become a log base 5 and equals x plus 2. You can immediately go to that step. The base of the exponential is the base of the log. What the exponential is equal to becomes part of the log, and then whatever the exponent was is what the log is equal to. So if you can keep all of that straight, you can skip a step and jump right to here. And from there, it's really the same process. So then x equals log base 10 minus 2, and etc., just like we did on the other one. X is equal to negative 0.57. All right, so just another way to kind of look at it there. So that's those kind of equations. There's some other exponential equations that will involve some logs that we're going to solve. And I'll do one of them with you here. Get a little bit tricky. We did some in pre-calc, and they're always the one that inevitably I would have questions on